Algebra 2, 7-8, using exponential and logarithmic functions. So you say, Mr. V, well, I'll never use this math ever in my life. Maybe that's true. But here's one way that real people use exponential and logarithmic functions in real life. And we're going to use these formulas for exponential growth and decay. And I'm leaving a little bit of space here because I'm going to do a growth formula and a decay formula. So here's growth. Growth is f of x equals a times e to the k times t power. We'll write the decay one and then we'll label these. F of x equals a times e to the negative kt power. Okay, so a is going to be your initial value, your starting point there. K is your rate of continuous growth. Continuous growth. And then t is going to be your time in years, generally. So we're talking about time, years. All right, let's label this one. The labeling is going to be pretty much the same. Here we've got initial value, we've got time in years, but this k here is different. So we're going to label that one. The rest are the same as growth here. This is called, instead of rate of continuous growth, this is the rate of continuous decay. All right, so there are our formulas. Now let's see how we use these. So we're going to do an exponential decay problem here, example. So real life people have found out that the half-life of carbon the half-life of carbon 14 is 5,730 years. And so basically what this means is this substance, carbon 14, is in an object, and after 5,730 years, there's half this much carbon left in that object. That's basically, I think, how it works. If it's not exactly that, you know, it's something very similar to that. So don't take me to the bank here, but that's basically what that means here. So here's what we're trying to do. A, we're going to try to find the value of k, and B, we're going to find, we're going to write the equation for figuring out how long something has had this carbon 14 in it. How long something has existed, whatever. They use carbon 14 to date like fossils and various things. Okay, so first we're going to start with this equation in order to find k here. And the way that we're going to do this is we're going to start with the decay function here. So let's just write that down. Let's just write it over here. Equals a times e to the negative kt. Okay. And so now we need to figure out what is the value of k. Once we find the value of k, then we have pretty much everything we need for this equation. So let's find the value of k first. Here is our function, and let's go ahead and plug in some information here. So this first part is a little bit tricky. So let me write this down. So 0.5a equals a times e to the negative k, and then my time is going to be 5,730 years. Okay, so now I've written this out and you're like, what are you talking about? Let me explain it. Okay, so if we start with whatever the object is and it has a full amount of carbon-14 in it. All right, so if we go for 5,730 years, then there should be half that much carbon left. So that means that if A is the initial amount, which is the full amount of carbon, 14, then we multiply that by 0.5, then we get this many years away from the original. So we have that. So we have half the original left after 5,730 years. So that's why we set this up. That's probably the hardest part of the this whole example here, is just figuring out how to get this first part set up. And so now we just need to solve for k. The reason this works so well, 0.5 times the initial amount, and the initial amount here, is I can just divide a out of both of these and the a's go away. So now I have 0.5 equals e to the negative k times 5,730. Now what do? Is I raise each side, or I take the natural log of each side. Natural log of 0.5, and then I also take the natural log of e to this mess. And when I do that, I get the natural log of 0.5 equals, so natural log, so this is the natural log of e to the negative k times 5,730. So the natural log of e, so remember our properties, those just go away, and I end up with k times 5,730. Now, all I have to do is divide both sides by this 5,730, and I'll find out what this is. And then I'm going to also have to deal with this negative here. So maybe I'll also I'll just divide it by negative there. And so that way those negatives will go away and I can deal with this. So I can get my calculator out. And I'm going to say natural log of 0.5 equals this. So that's what I have up here in the numerator. Now I'm going to divide by negative 5,730. Divided by 5,730. I'm not worried about the negative. I'll just figure that out in a minute. So now, so I'm going to ignore this negative because I didn't put the negative into my calculator. K is approximately 0.1230. We'll just leave it like that. That's fine. Okay. So that's K. So value of K is approximately 0.3012 there. All right. So we got that part. Now we need to do the equation. So now all I need to do for my equation is to plug this into it. So I've got f of x equals a, which is my initial amount, whatever that is, times e to the negative 0.00012 times t. And that would suffice for your equation. That's it. That's how you do that. So it's kind of complicated there, but that's okay. All right, so let's do another one here. So this was our example that we did together. And here is a U-try. Why not? Let's just do a U-try. Let's jump into it. So I've got the half-life of plutonium. Plutonium-239 is that specific type of plutonium, I guess, is 24,000 years. All right, so I want what K equals, or K is approximately. That's what I want. All right, so go. All right, let's see how you did. I'm going to use this as an example to help me wrap my mind around what I'm doing, okay? So half-life again, so I'm going to say 0.5 of however much I start with equals however much I start with after this many years. 24,000 years times, oh, I forgot to put the K right here. There we go. Now I just solve for K. So what I do here, I divide A out of here. Yay. Now I just have one variable left to solve for which to solve. 0.5 equals e to the negative k times 24,000. Take the natural log of both sides, so I'll write that out. 0.5 natural log of e to the k times 24,000. And then the natural log of e, all this stuff comes down here, this goes away. So I have natural log of 0.5 equals negative k times 24,000. Divide both sides. I'm going to divide by negative again, so to get that negative out of there. All right, now I just plug this into my calculator and I will know what k is approximately. Here we go. Natural log 0.5 divided by 24,000, and then I need to pay attention to my negative here too. So that is approximately 0.0, let's see, 4 zeros here. 1, 2, 3, 4. 29. Okay, now, so there's my value of k. Now, what we should have done on this first example, but we didn't, is we should, since we're talking about scientific things, we should put this in scientific notation. So I'm going to count over 1, 2, 3, 4, 5 places. So really, in scientific notation, this would say k is approximately 10, oh, it's not, sorry, not 10, 2.9 times 10 to the 1, 2, 3, 4, 5 to the negative 5. So that's the way we should do that. So for this one up here, the value of k should be 1.2 times 10 to the negative 1, 2, 3, 4 to negative 4. So that's what our answer should look like up there. And that's what it should look like down here too. All right, a little bit of a reminder of scientific notation. Let's do a few more examples here. Let's look at carbon dating some more. This is not where carbons get together and talk about how they like long walks on the beach. This is about trying to figure out how old some material is, how long it's been on the planet. So there's an animal that contains, okay, let's see if we can write this out without writing too many words. An animal contains 2% as much carbon-14, we're just going to say C14 like that, as alive, as when it was alive. Okay, so I'm just abbreviating a whole bunch so we're not writing so much. How long ago did the animal live? Okay, so let's see how we're going to set this up. So we say f of x, but we can use y. That's fine, either, too. So y equals a times e. Now, we know the rate of decay for carbon-14. We already figured that out here. It's 0.00012, right? So we're going to write negative 0.00012 times t. So that's the formula we're going to use for carbon-14, for the decay of carbon-14. So here's what we do, 2%. So if we're going to write 2% as a decimal, it's 0.02. Remember 1, 2? So 0.02. So all I'm going to do is write 0.02 times my initial amount. That's how much carbon was in the living animal. So here we have the living animal, E negative 0.00012, and I'm trying to find out the time. That's what I'm going to solve for. How long ago did the animal live? So we're going to find out how many years it takes for the animal to decay, or the C14 to decay all the way to 2%. All right, so we say we divide by A, 0.02 equals e to the negative 0.00012 times t. Now we're going to take the natural log of both sides because we've got this e to get rid of. So natural log of 0.02 equals natural log of e to the negative 0.00012 times t. The natural log of e gets eliminated there. So I've got natural log of 0.02 equals negative 0.00012 times t. Divide both sides by negative 0.0012. Oops, not enough zeros there. There we go. Divided by negative 0.00012. And then I'm going to find out what t is. So t is approximately, let's find out. Natural log of 0.02 equals, and that's a negative number, so when I divide by this negative, then it'll be positive. So I'm going to divide by 0.00012, right? 3 zeros, okay. And I end up with positive 32600. We're just going to leave it at that. Years. So this animal lived 32,600 years ago, according to our formula here. That the rate at which the carbon-14 left this animal after it died, that rate shows us that when it got to 2%, it had been dead for 32,600 years. Okay, let's do a couple more examples here. All right, now this animal, so we're going to do U try here. This animal is 20,000 years old. How much carbon-14 should be in the animal? Well, the animal's body, right? We know how long it's been dead, really is what we're saying here. How much C14 should be in the animal? In the animal's dead, lifeless body. Okay. So I'll talk about it for a second before you get started on here. So here's what you know. You know the 20,000 years. And now we need to find out how much carbon should be in this animal. when you set up your equation, this a value, when it started, right, so this is the beginning, you can put just a 1 for the a value because that's the initial value. And then you can solve the rest. Hopefully, we'll see. All right, go ahead and pause and see what you can do. Go. Okay, let's see how you did. So my equation is y equals a times e to the negative 0.0012 times t. All right, I know what t is, 20,000, bop. And I told you that you can plug 1 in here for a because that's the beginning of the end of this animal. So we're going to say y equals 1 times e to the negative 0.0012 times t, which is 2,000. And so we're going to try to solve for this, which is the amount of carbon-14 left in the animal after 20,000 years. Whew. So the 1 I can ignore. And now all I have to do here is grab my calculator. I push this little second and this e button here, e to the negative 0.123012 times 20,000. 1, 2, 3, close parentheses, enter, and I should have about 0.09, which is 9%. And that's it. That's all there is to it. Probably easier than you thought it might be, right? Okay. Now, let's go ahead and do one exponential growth example, and then we'll be done. So in 2007, population of Georgia was 9.36 million people. In 2000, the population in Georgia was 8.18 million. Okay, and I want to know what is the rate of exponential growth. So let's remember what is the formula for exponential growth right there. So it is f of x, or y, equals the initial amount times e to the kt. All right, so we know some of this information here. We know that this has been 7 years, so we're going to plug 7 in here. We don't know what k is yet. We know the initial amount at the beginning of the 7 years is, well, I'll just draw an arrow from here. 8.18 million, and then the amount that I got after those 7 years is 9.36. So I'm going to write this all out without the arrows. 9.36 million equals 8 point, oh no, I did that, yeah, no, I did that right, okay. The initial amount is the 8.18, and times e to the rate, which I don't know, and I'm going to find out soon, hopefully, times 7. And now we solve this just like we did the decay problems that we did. I'm going to divide, and so I'm going to get a disaster over here equals this. So am I going to, yeah, I'm going to leave, no, I'm not going to leave the disaster. All right, I'm going to put this in my calculator. 9.36 divided by 8.18, and I get, ew, gross. Oh, that's the problem. I didn't put the point on the 8. All right, 9.36 divided by 8.818. 0.18. All right, that's right. Okay, so I get 1.1443 approximately over here on this side. And then I'm going to say the natural log, I'm going to take the natural log of that, and I'm going to take the natural log of what's left over here, which is e to the k times 7. That goes away, so I'm left with k times 7 over here, natural log of 1.1443 equals k times 7. So I'm going to divide both sides by 7, and I will find out what k is. K is approximately the natural log of this number divided by 7. Natural log 1.1443 close parentheses divide by 7 equals 0.01926. And that is the rate of change here for exponential growth in Georgia. Now we can write it as in scientific notation as well. 1, 2, move that over. 1.926 times 10 to the negative 2. That would be fine as well. All right. And that is all of the notes we are going to take for 7-8. Good luck on the homework, people.